This begins EE 555 with Dr. Zahid. It's January 16, 2014.
Welcome back to E555. Let's continue our overview about the topics that we will be covering throughout the course. We started looking at the components of a broadband network, and we said that we have the user network. The user can be a corporate network or a residential network. We do have the access network. The access network is a network that connects the user network to the service provider network. Could be wired access using DSL or cable or fiber to the home or the passive optical network, many technologies that we will study in detail as we move along. Or it could be a wireless access, the broadband wireless access, the WiMAX, the Wi-Fi, and the cellular, the 3G, 4G cellular access. Then we do have the metro and the core. Again, the difference between these are both backbone networks. The metro covers metropolitan area network. The core covers the backhaul, the long distance network. The metro and the core mostly are optical fiber with the different technologies, the SONET, the WDM, the MPLS, IP, Ethernet, and so on and so forth. All of these we will be, again, studying them in detail as we move along. And then there is the back end, which contains all the types of all types of servers, content providing services, web services, video services, and so on and so forth. These are the servers that the users are trying to access to achieve or to get a high bandwidth or bandwidth intensive type of applications like video on demands, like gaming, and so on and so forth that they are trying to get beyond the conventional services. Now, most of the efforts currently, were on the core and the metro network, trying to increase the capacity of the core, of the backbone. The problem with this statement is that the access remains to be the bottleneck. See, for example, if you look at ADSL, let's see if you remember from the ADSL, from 450. First of all, ADSL, there is a limitations on the distance between the customer network and the service provider network. The distance is roughly about what? Roughly about 15,000 to 18,000 feet. So the distance between this one and the central office has to be within a certain distance. Otherwise, the digital signal will be degraded as it moves along. ADSL, again, currently on the downlink, maximum of what? 8 megabits per second. On the uplink, maximum of roughly what? 1 megabits per second. By the way, even that 8 megabits per second, most of the time you are not going to achieve it. Now, I want you to see this, and I want you to see this. In the backhaul, we are talking, for example, about OC192, which is 10 gigabits per second. All the way to OC, for example, OC768, 40 gigabits per second. And tell me, what do you see? Do you see a problem? Do you see a problem? This is the backhaul. This is the backhaul. This is the backbone, the metro network, for example, whereas this one is the what? Is the access network. Do you see a problem? We see a problem. The problem being what? Is that the bottleneck will always be the what? Will always be the access network. So it does not make any difference if you increase the capacity of the core network tremendously if the access network remains what? Slow. Because that will be the bottleneck in the what? In the end-to-end connections. Clear? Okay. So this is the problem with the DSL, for example. By the way, even with cable, we'll get to this in just a second. Even with cable, you know that a cable is a shared network. As the number of users increase, as the number of residential, for example, customers increases, the rate that is available to each user will go what? Will go down. You follow me or not? Yes? It will go down because it's a shared network, a cable, on the uplink. It makes what makes the users a little bit frustrated. How many of you have cable access? None of you? How much rate do you get? Can you raise your voice a little bit? Let's say 16 megabits per second. Yes, as you said, 16 megabits per second. Does it compare to these? So it's still what? It's still that it behaves as a bottleneck, whether it's ADSL or whether it's what? Cable. Cable is much better than the ADSL because it has a wider bandwidth, but it's still not enough to what? To support those higher data rates or those applications that are bandwidth intensive or bandwidth hungry, that it needs a much wider bandwidth. And hence the trend is toward what? Is toward extending the fiber all the way to the home or extending the fiber to the curb and so on and so forth, as I will show you in just a second. Okay. Now we started with DSL. Again, as I told you, the traffic will be coming from different users and they are going to be what? What did we call this? We call it DSLAM. DSLAM stands for what? The digital subscriber line access multiplexer. Let's see if you remember what kind. Let's see if you still remember. This from 450, multiplexing. How many types of multiplexing do we have? Time division. We have synchronous, TDM, and we do have what? Statistical, TDM. Time multiplexing, which is the one that is most widely used for digital transmission. Statistical TDM, also known as concentrate. Does this ring a bell or not? Yes? Let's see if you can tell me what is the difference. This is a MUX. This is a synchronous MUX. Okay, these are the time slots. What do we say in synchronous MUX? Time slots are pre-allocated to what? To each channel or user, regardless of the activity of each user. And we saw that the rate, the multiplexer rate, is what? Greater than or equal to the summation of what? R sub I. I goes from 1 to N. N users here. N chance number 1 all the way to what? Number N. Clear? Okay. What is the statistical MUX? Same thing. But the time slot now is what? The time slots are allocated on a what? Per demand basis. Okay. Each one of these, by the way, is a what now? Is a header, because the time slots are not pre-allocated. And what was RM here? The multiplexer is less than the summation of R sub I. I goes from 1 to N. Less than. This is what we referred last time as what? Oversubscribed. Oversubscribed. You are going to what? You are going to allow multiplexing of several users using what? Using a rate which is less than the aggregate rate. Let's do some analysis here. Let's see how much you remember from 503. some analysis. All of this you should have had it in 503. Let's see if you remember. Okay. Remember, we are talking about this one here. We are talking about this device here that will aggregate the traffic from several customers. Okay, let's take some example here. Consider, let's say, 5 sources connected to a statistical time division multiplexing. S stands for what? Statistical. Each source generate traffic according to an on-off model. On and off model, what does it mean? It means that a source for some period of time, it is what? Active. For some period of time, it's what? It's idle. Clear? According to an on-off model. Okay, when active, each source generate, let's say, traffic at a fixed rate of, let's say, landed packets, let's say, per minute. So when the source is active, it generates traffic at a rate of landed packets per minute. Of course, when off, when idle, it generates how much? How much? 0, of course, 0 packets per second. That's all, per minute. Okay, each source is active for a period of time that is exponentially distributed with parameter let's say beta, and idle for a period of time that is exponentially distributed with parameter alpha. Does this ring a bell or not? You remember the exponential? Let's see if you remember, recall. Exponential. PDF is what? Let's see if you still remember. Fx of x okay, a gamma, for example, gamma e to the minus gamma x for x greater than or equal to 0. You remember this? Okay, good. Now, and the question tells you what? A model, a sketch or a model V, aggregate, traffic, and find the total rate at output of mux for a synchronous. TDM, B, statistical. TDM. Clear? Clear? Okay. Now, let's look at the synchronous TDM first, because that's very simple. In synchronous TDM, what do we say? Does it matter about the activity of the sources? Does not matter on the activity of the sources. Each one generates at what rate? At what rate? Where is it? Here. Generate at a rate of what? Lambda. How much do we need? How much do we need here? So we need what? Here the answer to this is what? 5 lambda. Did you get this or not? We need the rate of the mux. We need the rate of the mux, the rate of the synchronous multiplexer to be what? 5 lambda. Did you answer where this came from? Yes? Okay, good. Now, for statistical. Now, modeling of each source. Each source could be modeled as follows. How many states do we have? This is a Markov chain. How many states do we have? We have 2 states. Either what? Idle, let's call it 0, or what? Active. So this is idle. This is what? Active. 2 states. Yes? Now, it will remain idle for how long? For an exponentially distributed period of time with parameter what? With parameter alpha. So what do I put here? I put alpha. This is the rate of transition. Or the rate of transition. In other words, at the end of the idle period, you are going to transit to what? To the active period. And similarly, from 1 to 0, it will be what? Beta. Clear? This is for one source. This is for one source. Okay. Now, for all sources. Okay. Let n be the number of what? Active sources. The number of active sources. Okay. Now, how many states do I have? How many states do I have? I have n is the number of active sources. Total number of sources is how much? 5. Let n be the number of sources, active sources. Yes? So we have 6 states. What are they? 0, 1, 2, 3, 4, and 5. Clear? Clear so far? Okay. Now, let's see if you can help me. Let me sketch first of all the arrows. You all studied Markov chains in 503, right? No response. Let's see if you can help me. Let's start with this one here. Yes? Let's start with this one here. How many sources are active? 1. Yes? Now, when this transition goes to 0, what does it mean? It means that active source has what? Has stopped talking or has stopped generating traffic. Clear? Has stopped generating traffic. So what do I write here? What do I write here? I write bait. How about this one? Oh, how many traffic sources are active? 2. Yes? One of them stopped generating traffic. Which one? Which one? The one that has the minimum active period. Yes? What do I write here? 2 bait. Why? Let's see if you remember. Sometimes it's frustrating. Aside. Let's assume I tell you Z is the minimum of X, Y. Z equal to the minimum of X comma Y. This is a random variable, which is a function of two other random variables. Z equal to the minimum of X and Y. If X is exponential and Y is exponential, they are independent. If X is exponential and Y is exponential, what will Z be? Z will also be what? Exponential. Z will also be exponential. But with what parameter? If the parameter of this one is beta, and if the parameter of this one is beta, then the parameter of this one will be what? 2 beta, the sum. Clear? You remember this? So what do I have? 2 beta, 3 beta, 4 beta, 5 beta. Tell me now, what do I do with this? What happened in here? What happened in here? I have all what? All the sources are what? Idle. And suddenly, one of them started what? Generating. Which one? Which one? The one whose what? Whose idle time is the what? Is the minimum. So what do I have here? 5 alpha, 4 alpha, 3 alpha, 4 alpha, 5 alpha. Did I make a mistake? No. 2 alpha. I'm sorry. 2 alpha. And this one is what? Alpha. I'm sorry. Clear so far? Clear so far? Okay. Now we write the what? We write the balance equation. Writing the steady state. Steady state. Balance equation. Help me. Help me. Let's look at this. Here, for example, what do I have? What do I have? Beta times P1. What does P1 means? What does P1 means? P1 means what? The probability that there is a what? One active source. Beta times P1 equal to what? 5 alpha times what? P0. Did you get it? Did you get it? This is the balance equation on this boundary. It's beta times P1 equal to what? 5 alpha times what? P0. Clear? Okay. Which means what? It means P1 equal to what? 5 alpha over what? Beta times what? P0. Now let's do another one just before we generalize it. Let's look at this boundary. What do I have? Tell me, what do I have? Give it to me. 2 beta times what? P2 is equal to what? 4 alpha times what? P1. Did you get it? Okay. Which means what? I want to write everything in terms of P0, which is equal to what? P1 is what? Is 5 alpha, so it's what? 5 times what? 5 times what? 4 times what? Alpha square over beta times what? Did you lose me? Okay, one more time. 2 beta P2 equal to what? 4 alpha P1, and P1 is what? Is 5 alpha, so it's what? 5 times 4 alpha square beta P0. Yes? Which means what? It means P2 equal to what? 5 times 4 over what? 2 times what? Alpha over beta square times what? P0. Did you get it? Did you get it? Can you generalize it? Can you generalize for me? What is generalizing? Do you see a pattern? What is P sub K? First of all, what is P sub K? And worse, what is it? It's the probability that N, which is the number of what? Number of active devices equal to what? K. Where K goes from where to where? 0, 1, all the way to what? 5. what is it equal to? Do you see a pattern? Do you see a pattern here? Look at this. 5 alpha over beta P0. When it is P1, P2 becomes what? 5 times 4 times divide by what? 2. Do you see a pattern? What will be 3B? What will be 3B? P3 will be what? 5 times 4 times what? 3 times what? 2 times 1. Alpha over beta squared times what? P0. So what is it? Can you generalize it for me? 5 choose what? K times what? Alpha over beta to the what? K times what? P0. Did you get it or you lost me? This is all 503. Did you get it or you lost me? Okay, good. Now, what is the unknown? What, I mean, am I done or I need one more equation? Let's put this one, equation 1. I need to find what is P0. Yes? So what is the other equation? Summation of P sub K. K equal to 0 to what? 5 has to be equal to what? 1. Which means what? Which means the summation of K equal to 0 to 5. K equal to 0 to 5 of what? 5 choose K alpha over beta K P0 is equal to what? 1. Can I get the P0 outside? So what is the P0? 1 over the summation of K equal to 0 to 5 alpha, 5 choose K times what? Alpha over beta to the what? K. Did you follow me so far? Are you following me so far? And that's equal to what? Now I'm going to write this like this. Let's see if you can help me. If you can follow me here. 5 choose K times alpha plus beta K times beta alpha plus beta to the 5 minus K. Let's see if you can help me here. I'm not done with this. Let me see if you can help me. 5 choose K is this 5 choose K. Yes? Alpha to the K is this alpha to the K. Beta to the K is this beta to the minus K. Did you get it or not? Okay, so what do I have here? Alpha plus beta to the K will cancel with what? Alpha plus beta to the minus K. Do you agree? So what remains? Which term remains? Which term remains that is not here? It's beta over what? Alpha plus beta to the what? 5. I'm going to put it here so that they will cancel. Did you lose me here? You lost me here. Concentrate. I want to change this format into another format. The 5 choose K is this 5 choose K. Alpha to the K is this alpha to the K. Clear? Beta to the K, beta is in the denominator. Beta to the K is this one. Beta to the minus K. Beta to the minus K is what? 1 over beta to the K. Agree? Okay. Alpha plus beta to the K will cancel with what? Alpha plus beta to the minus K. So what remains in here that I added is what? Beta over alpha plus beta to the what? 5. I need to multiply with this because that term is not here. So I need to multiply with this so that they cancel. Clear? Now what is the denominator? Can you tell me what is the denominator? Equal to? Still waiting. I want you to see this. Alpha over alpha plus beta, and this one, which is what? Beta over alpha plus beta. What is this equal to? 1 minus alpha over what? Alpha plus beta. You agree? So what is this? That's a binomial. Yes? That is a binomial. And I'm adding between what? K equal to 0 and what? 5. So what is this? 1. That's equal to 1. This is a binomial. The binomial PMF. What is PMF stands for? PMF stands for? No response. Probability mass function. This is for discrete random variables. So what do I get? I get P0 is equal to what? Beta over what? Alpha plus beta to the what? 5. Notice, by the way, P0 is a constant. It's not a function of K. Clear? What is P0, by the way? What is P0 in words and words? The probability that all devices are what? Idle. Are you following? The probability that all devices are what? Idle. Notice, by the way, if all of them are idle, it means what? It means the capacity of the multiplexer link is what? Is wasted. Are you following? Nobody is using it. Why? Because all devices are what? Are idle. Clear? Okay. So now, what do I have? I have P, the probability of K is equal to what? Where is it? Where did I write it? Here. Where did I write it? Okay. So it's 5 choose K times what? Alpha over beta K times what? P0, which is what? Beta over what? Alpha plus beta to the what? 5. And again, K equal to what? 0, 1, all the way to 5. Now I can rewrite this as what? 5 to the K, 5 choose K, alpha over alpha plus beta to the K, same idea, beta over alpha plus beta to the 5 minus K. Is this the same as this? Let's see. 5 choose K is this, 5 choose K. Alpha to the K is this. Beta to the K is this. Beta to the minus K means what? This. Then what do I have? Alpha plus beta to the K will cancel with what? Alpha plus beta to the what? Minus K. Yes? So what remains? What remains? Alpha plus beta to the what? Which is this one? Did you get it? Okay. What can you tell me about K? Remember, P, this means what? Probability that N equal to K. Hence, N, which is the number of what? Active devices, is what? How it is distributed? Is binomial with average value of what? What is the average value of a binomial? What is the average value of a binomial? What is the N here? 5. What is the P? Alpha over what? Alpha plus what? Beta. Did you get it or not? Okay. Let's see if you can tell me here, first of all. Where is the lambda here? This is generated traffic. Lambda. Here is what? What is it? 2 lambda. Here is what? 3 lambda. Here is what? 4 lambda. Here is what? What is the average? What is the average aggregate traffic? What is it? 5 lambda times what? Did you get it? You struggled here. Did you get this? Why did I multiply by alpha? This is on the average. This is how many what? How many devices are active. And when they are active, what do they generate? They generate traffic at a rate of what? Lambda packets per minute. So what is the average traffic generated? Aggregate is the average number of what? Devices that are what? Active multiplied by what? By the rate that they are generating. Clear? I want you now to compare this with this. Tell me what happens. Which one is larger? This one for the synchronous TDM or for the statistical TDM? Synchronous TDM is larger. Are you following that? Why? Because this one is taking into account that some devices are going to be what? Idle. I don't need that higher rate at the output of the multiplexer. Clear? At the output of the multiplexer. Because he is taking into account that some devices will be what? Idle. Clear? So this is the what? This is the capacity, if you would like, or the multiplexer. Right. Now, what happens if for a short period of time all of them are active? Could they be all of them active? Yes? What rate would we need? 5 lambda. How much rate do we have? We have less than 5 lambda. Yes? What will happen? What will happen? The Q, let me show it to you so that you can see what I'm talking. Jump with me to page 76, please. What will happen? This is the server. This is the incoming traffic. If the aggregate arrival rate exceeds the what? The service rate. If the aggregate arrival rate exceeds the service rate, what will happen? That queue will begin to what? Will begin to pile up. And if you reach the capacity of the queue means what? How many packets can be what? Can be stored in the queue? You are going to what? You are going to drop the packets. Clear? You are going to drop the packets. We'll talk about that when we get to the quality of service shortly. Did you understand it or not? Did you understand? This is a simple analysis. I thought to bring it to you at the beginning so that you understand where the 503 will get into the picture. This is the 503. This is what you studied in 503. Now let me know, again, as I told you, Angelos will give you some more review about queuing in next week, in this coming week discussion session, but I might also need to set a couple of extra classes, not regular classes, make-up classes, to review some queuing models for you. It looks to me like you struggled a little bit here, but in any case, did you struggle? Yeah, this is a question, yes or no? Okay, I think you struggled, but in any case, I just wanted to bring it to your attention. Okay, so this is the ADSL, getting back to our discussion. This is the ADSL, and this is, again, as I told you, the cable. This is the cable. And again, as I told you last time, the cable is a what? It's a shared media, which means what? As the number of what? As the number of customers increases, what will happen? Each one will get a what? Lower rate. Why? Because you do have a what? Fixed shared capacity. Capacity of the cable is going to be given to what? Given to all users. Clear? The good thing about cable is that they don't have that distance limitation that the ADSL has. ADSL, as I told you a moment ago, that the distance between the customer network and the service provider network cannot exceed roughly 15,000 feet. For cable, it's what? It's much longer than that. Why? Because cable, you are going to be transmitting your signal within a what? A thick coaxial cable, which is more immune to noise or interference from outside. Whereas ADSL, you are going to be transmitting over what? Over copper wire. Clear? Oh. The next says what? They said in order to remove the bottleneck, from the what? Access network, we need somehow to find solution of how do we extend fiber, because the fiber has a what? A huge ability to carry what? All of these bandwidth intensive application. The video on demand, high definition TV, the gaming, and so online gaming, and so on and so forth. So they decided to what? Extend the fiber to the cable. Extend the fiber to the cable. Extend the fiber all the way to the what? Either to the curb or to the what? To the home. So the first solution is what we refer to as the fiber to the cable, where we extend the fiber all the way to the cable, to the curb, and then we extend what? We extend copper wires. Copper wires to the home. But what did we say about this last time? This is not a pure end-to-end fiber. It's not a pure end-to-end fiber, because these are what? These are copper wires. But this one can support roughly, like I showed you last time, can support 50 megabits per second. 50 megabits per second. Why? Because these copper wires are what? These copper wires are short. We are talking about what? We are talking about 100 meters and so on. Clear? Roughly 100 meters. Clear? Okay. The next solution that we talked about is what? Is the fiber to the home. Extending fiber all the way to the what? To the home. Clear? What was the problem with this? What was the problem with this? The problem with this is that if we do have end users, how many optical transceivers do we have? We need 2 N optical transceivers. Clear? There are 2 N here, there are N here, and there are N here. 2. Now let's assume each fiber, let's assume this length here is L, the length of the fiber. How many fibers do we need? We need, still waiting, N times what? L fiber. Did you get this or not? Yes or no? Okay, this is, by the way, is a what? A point to point. From the customer point of view, do they like this? From the customer point of view, they love this. Why? Because each customer will only need what? One transceiver, one optical transceiver, and this bandwidth of this fiber is dedicated to that user. Did you get this or not? Who doesn't like it? The service provider doesn't like it, because he has to what? He has to deploy that many fibers, N fibers, NL fibers, and he has to have what? He has to have N optical transceiver in the office. Clear? Clear? What is this, by the way? This is the metro and the what? Metro and the core. In other words, this, by the way, they call it what? OLT. OLT stands for what? Optical line terminator. These here, you see those stars here? These are referred to as what? ONU. ONU stands for optical network unit. Optical network unit. Clear? So came what? Came the next favorable solution, which is what is known as what? Passive optical network. This is the one that is gaining momentum. Passive optical network. Now, first of all, what does passive means? A passive means what? There is no active element. There is no active element from what? From the customer all the way to the what? To the service provider office. No active elements. Clear? The passive, what they do is the following. They do have a single fiber. They extend a single fiber here. One wavelength at the beginning. One wavelength on a single fiber all the way to what is known as a what? Splitter / what? Combiner. Collectively, they call it a what? Passive optical coupler. Again, we'll study this in detail later on. I just want you to get familiar with the technologies that are used. Okay, now what do I mean by splitter and combiner? Are they opposite each other? Splitter and combiner, they are opposite each other. When are they splitter? It's on the downlink. On the downlink, they are splitter. What is it splitting? It's splitting the total power. Let's assume, for example, here, these are what? These are two fibers. This fiber was split into two fibers. What does it mean? If the power here is P, what is the power here? P over 2, P over 2. By the way, the power does not need to be divided equally. But for the sake of our discussion, let's assume it's equal, just for simplicity. Later on, we will discuss different things. Are you following me on that? So we have what? P over 2 here, P over 2 here. This one is another splitter. Each one of them will be what? Let's assume there we have 8 here. Then this one will be what? P over 16, P over 16, and so on. Now, when it will be a combiner? When will it be a combiner? It will be a combiner on the what? On the uplink. On the uplink, it's a combiner. Notice, by the way, this is a directional coupler. Directional coupler means what? Means on the uplink, look on the uplink. On the uplink, when this one comes in here, when the traffic comes in here, it will not go this way. Did you understand? It's a directional coupler. It goes in one direction only. Did you get my point or not? It's not going to come here. In other words, this user is not going to send traffic to this user. All the traffic is going to be what? Is going to come to the point. Clear? Now, let's see what is the good thing about this or not. Now, first of all, is this a point-to-point or is it a point-to-multi-point? It's a point. This one now is a what? Is a point to multi-point architecture or topology, if you'd like. Let's see how it works. Let's see how it works. Now, first of all, how many optical transceiver does it need? We need only one optical transceiver. Yes, in here, in here. So from the service provider point of view, he likes that. Clear? He likes that. How many fibers does he need? It's one fiber. Now, you might say, but how about those fibers? Those fibers are going to be what? Short fibers. Because this is extending very close to what? Very close to the residential community, to the curb or something like that. Clear? So the major thing, in other words, where is the L here? You see this L here? This L is actually this L. These are just shorter ones. So he only need to deploy what? L kilometers or L meters, whatever the units are of what? Of fiber. Clear? Okay. We still need what? We still need, of course, every user needs to have a what? An optical transceiver. So what is the total? If this is N, by the way, if this is N, what is the total? N plus 1 optical transceivers. Clear? N plus 1 optical transceivers. Did you answer what I just said or not? Now, on the downlink, oh, one more time, on the downlink, is it a broadcast? Is it a broadcast? Now, I want you to understand one thing. When we say a broadcast network, that is not the same as saying what? A broadcast traffic. A broadcast traffic or a broadcast application, it's a type in which every end user is supposed to receive that traffic. Are you following or not? When we say broadcast network, what we mean by that is what? Is that every NIC card, what does NIC stands for? NIC, network interface card. Every network interface card receives every transmission. You lost me again here. You forgot about the Ethernet? One more time. What is this? What am I sketching? Is this an Ethernet? Is it a shared medium? Shared medium. A, B, C, Z. A is transmitting something to B. Will C receives it? And C with the NIC card will receives it. Will Z receives it? Everyone will receive it. Are you following or not? Everyone will receive it. This is what is known as a what? As a broadcast network. There is no switching involved. There is no switching involved. Clear? Okay. However, which one will process the frame? Which of these will process the frame? Only B will process the frame, whereas all the rest are what? Are going to what? Drop it. Did you get this or not? So how does this one work? less. Now, most popular, by the way, most popular is what is known as what? EPON. What is EPON stands for? Ethernet Passive Optical Network. Why is this one most popular? The EPON. Why is it most popular? Think a little bit about it. Does this one look like this one? It looks like this one. Are you following or not? Now, EPON, what does it mean? It means the traffic, the downlink traffic will be encapsulated inside what? Ethernet frames. Will be encapsulated inside what? Ethernet frames. And the Ethernet frames will be transmitted over what? Over the fiber. Did you get my point or not? Yes or no? Okay. Now, each packet or each frame is going to be addressed to a certain what? A certain destination. Are you yes or no? Now, when this one is split, will this one receive all the traffic? This one will receive all the traffic, but it will only process what? Those frames that are what? Directly addressed to it. All the others are going to be what? Are going to be filtered out. Did you get my point or not? All of them, by the way, over a single wavelength. This is not wavelength division multiplexing. Just what? One wavelength. Did you get this or not? You are multiplexing several traffic on the downlink, several traffic on a single wavelength. This traffic, some of it will be what? Destined to this, some of it will be destined to this, and so on and so forth. Clear? Now, on the uplink, do we have a problem? What is the problem? Let's look first of all on here. In here. Can this one and this one transmit at the same time? What will happen if they transmit at the same time? Collision. What was the protocol that we used in EE450 to what? To do something about this. What did we call it? Let's see if you remember. What does CSMACD stands for? Carrier sense multiple access with what? Collision detection. Can we use it here? Can we use it here? The answer to that, no, we cannot. Why? Let's understand why. This is going to be transmitting traffic. All of them the same wavelengths. We are not talking about different wavelengths. If they are different wavelengths, there are no collision, as I was showing just a second. We are talking about the same wavelength. On the uplink right now. On the downlink, we don't have a problem. Why? Because the traffic is coming from where? From one point, just like in cable. It's coming from what? The service provider office. On the uplink, this one is a transmitting. Yes? This one is a transmitting. At the same time. Yes? They will be combined here. At the what? Combiner. At that coupler I told you about. Yes? Will there be collision? There will be collision. But how do they know about it? The collision came after the coupler. And the coupler is what? Directional coupler. Did you get my point or not? Now, one possibility, who will detect the collision? Who will detect the collision? The optical line terminator will detect the collision. Did you get my point? He will detect the collision because he is what? On this side of the coupler. Yes? Now, he could send a what? Collision detect message to what? To all of them. Did you understand that or not? But what is wrong with this statement? Or what is not so good about this statement? The distance in here, remember this is fiber here. We are talking about distance exceeding what? 20 kilometers and so. Every time a collision occurs, this one will be sending a what? A collision detect message over what? Over what? Over 20 kilometer fiber? You lost me here. Did you lose me? It's a lot of what? A lot of overhead, and it will what? Bog down the network. It will bog down the network with what? With the propagation delay all the way from where? All the way from the optical line terminator to each one of these devices. Yes or no? One more time. Where did the collision occur? Can you show me where is the collision pictorial in the picture? Where did the collision occur? Did it occur here or after the combiner? After the combiner. So how does this one sense it? How does this one sense it? In here in Ethernet, when a collision occur here, that collision will propagate all the way to the what? To the end of the buses, and each one of these nodes will detect the collision. In here, the collision occurred in here, but the collision cannot go this way. Why? Because the coupler is what? Directional. It's in one direction only. It's not two directions. Clear? So this one will detect the collision. Every time a collision, this one will what? Needs to send a collision detect message to each one of them, traveling over distances of 20 kilometers. Does not make sense. So what is the solution? And we'll talk about this later on. It's just an overview. The solution is what? Is that the OLT will what? By the way, all of these will synchronize their clocks with what? With the OLT. With the OLT. The OLT will divide the usage of the fiber in what? In time slots. And he is going to assign time slots on the uplink, to each one of these what? To each one of these users. Clear? Those time slots could be assigned on a permanent basis using synchronous TDM, or they could be assigned on a what? On a per demand basis using statistical time division multiplexing. Now the question is what? But how does he know which one of them is active or not? Each one of them will be sending on the uplink some kind of what? Some kind of message telling him how big the size of the queue. How big the size of the queue means what? How much traffic? How many packets are there in the queue waiting to be transmitted? More packets means what? I'm going to give you more what? More time slots. Less packets means what? I'm going to give you what? Less time slots. Clear? Clear? Okay, but we'll talk about that later on. Now, what is still a problem with this? There's still a problem with this is that eventually, by the way, can we have a large number of what? A large number of users? I want you to think a little bit about it. What did I tell you about the splitter? I told you that the splitter will going to divide the power into what? It divided by what? N users. As you increase N, the power to what? The power to each one of them will be what? Will be limited. Alpha will be reduced, which means what? You need to what? Amplify it along the way. Did you get this or not? Okay, so currently roughly between what? 8 to 32, maximum defined in the standard is up to 128. Clear? Okay. The other issue here is that we are still using what? One wavelength per fiber. One wavelength per fiber. But the capacity of the fiber is much more than what? Just one wavelength. Can we support multiple wavelengths? Can we support multiple wavelengths on the same what? On the same fiber. Clear? Notice, by the way, if you support multiple wavelengths on the same fiber, let's assume in here, instead of just lambda 1, you put what? Lambda 1, lambda 2, lambda 3, lambda 4. You could even assign to each of these users a specific what? Wavelength. And in this case, even though the topology, the diagram did not change, but it is no longer a what? A point to what? Multi-point. It is now a what? A point to what? To point, without extending what? Multiple fibers. It's the same fiber, but it's a different wavelength, which means when this one is transmitting at lambda 1 and this one is transmitting at lambda 2, when they get combined, do they collide or they do not collide? They do not collide, which means as if you do have what? Look at my finger. As if you do have this path. Is that a point to point? That is the point to point, logically. But physically, it's a what? It's a shared media. It's a shared media because we are not going to use what? Multiple fibers here. We are going to use only one fiber. Clear? Clear? That is the concept that I told you about last time. We'll get to the wireless in just a second. That's the one that I told you about using the what? Using what is known as what? Wavelength division multiplexing. So the difference between TDM and WDM, what is this? Let's look at this. This is TDM. A single fiber we are going to divide its use in what? In time. So we do, in here, how many time slots do we have? In here, look at the diagram. How many time slots do we have? N time slots on a single what? Fiber. Yes? Let's assume, just for the sake of argument, let's assume that the fiber is what? 10 kilobits per second. Did I say 10 kilo? I'm sorry. 10 gigabits per second. 10 gigabits per second. And if there are what? 10 channels, then each channel can support how much? 1 gigabits per second. Yes? This is time division multiplexing. This is what? Wavelength time, a wavelength division multiplexing. What do we have here? We have a single fiber, but it is supporting how many wavelengths? N wavelengths. Are you following or not? And every wavelength can be what? Divided into what? Sub-channels. Are you using what? Using TDM. Did you get this or not? Which means what? The aggregate capacity will be what? Which means will be much higher. Are you following me or not? Will be much higher. Clear? Clear? That's the concept of the wavelength division multiplexing. You could have, for example, you could have 4 wavelengths. You could have 16, 32, 64. And again, as I told you, currently some service providers are deploying 160 wavelengths. 160 wavelengths for what? Just a single fiber. To them, is that good or bad? To them, to the service provider. It's good. They don't like to extend fibers, because when you extend fiber, you need to take what? You need to take licenses from the city. You cannot just go overnight. Everybody is sleeping. Let me extend the fiber. Cannot do that. You need to take what? Licenses. You need to pay fees and stuff like that. Clear? People come and dig the ground so that they install the fiber underneath the ground, or they build a cabinet to put the fiber through, and so on and so forth. It's too much headache to them. Clear? Okay. So the wavelength division multiplexing, which we'll be studying later on, allowing what? Allowing multiple, you know, by the way, this one is totally what? Optical. Whereas this one in here, there are some of them are what? Are digital signal. DS stands for what? Digital signal level 1. Anybody knows what this one is? DS1? This is a what? T1. Do you remember the T1? What is it? The rate of T1? What is DS3? Anybody? Okay, once you finish with the T3, then becomes what? Becomes all optical. Whereas this one is all what? Optical. I'll explain to you later on what is the C stands for. It stands for concatenated. Let's not worry about that right now. This is called, what is AGM stands for? From last time? You are struggling. The struggle has started already. ADM stands for what? Add. Mux. Okay. This is, again, several wavelengths. Each wavelength is what? What type of a multiplexer is this? This is a what? This is a sonnet type multiplexer. Are you following me? A sonnet type multiplexer, a TDM type multiplexer, whereas this one is a what? Is a wavelength division multiplexer. Each wavelength is divided in time, and then this one will multiplex what? Wavelength. Does not multiplex time slot. He is multiplexing what? Wavelength. These are multiplexing time slots. Clear? So a single pair of fiber supporting multiple wavelengths. We'll get to this in just a second. Clear so far? Okay. Notice, by the way, in the plan, if you are going to use wavelength division multiplexing, you don't need to use wavelength division multiplexing both on the uplink and on the downlink. You can use what? In other words, they could on the downlink, you could have what? Wavelength division multiplexing on the downlink. But on the uplink, you could have what? Just a single wavelength. Do you follow me or not? Okay, so I mean, you know, it depends on the deployment, how they deploy the equipment. Remember, by the way, if you go to the wavelength division multiplexing, you need to have the right equipment, which is the what? The wavelength division multiplexer. You need to install those. In addition to the what? Optical transceivers. Clear? Okay, but the good thing about it is that you are not going to increase the number of what? You are not going to increase the number of fibers in there. Clear? No response. Clear? Oh. Then we looked at, briefly, again, we'll discuss this in detail later. We looked at, we are still in the access network. We looked at what? We looked at the wireless access network. We said that most popular of them is, of course, the Wi-Fi. It could be infrastructure type, where all the communications will have to go through the AP. Whereas the ad hoc, they are going to be able to communicate with each other. Which one is more efficient, by the way? Can you tell me which one is more efficient? The ad hoc is more efficient. Why? Because the ad hoc communications can be what? It can be directly. In other words, if this one wants to communicate with this one, it has to go through the what? AP, and then the AP will what? Relay it to this guy. Whereas this one, you can go directly in here. And the question with this is that it's going to be limited range in this case. So if you want to access, for example, the internet, you have to go through what is known as a relay. Everyone will relay the message to the other one, to the next one, to the third one, until you reach what? Until you reach a position in which you can access either through what? Either through the WiMAX, which is a longer distance, or through what? Through the infrastructure itself. Through cable or ADSL and so on and so forth. Clear? Clear? Okay. Let me make one comment in here about this. I need you to understand what the issue here. If they say, for example, IEEE, just an example, IEEE 802.11g, just an 11g. You remember how much the rate? You don't remember the rate? The rate is what? Maximum rate. 54 megabits per second. Is this the aggregate rate, or each user gets 54 megabits per second? Or is this the aggregate? This is the aggregate. Are you following or not? You have to remember that within, for example, in here, if this is the only one who is sending, if he is the only one who is sending, he will get how much? Theoretically, he will get 54 megabits per second over this link, over this short link. Are you following me or not? But this guy is not to be the only one he is going to be transmitting all the time. So this 54 megabits per second is not going to be all the time. The more users there are, each one of them will get what? On the average, will get what? Less and less. Are you following me or not? Always remember when they talk about shared media, like cable, for example. If the gentleman said a moment ago 16 megabits per second or something, this is what? This is aggregate thing. Every time users comes more onto the medium, the rate for each one of them will go what? Will go down a little bit. Clear? Okay, good. Now we'll talk about all of these later on in the semester. We went then into the metro and the core network. We said that the metro, most of the metro is a what? Is a sonnet ring type. You see the ring topology? Okay, we come gathering traffic for where? Where is this coming from? The traffic. The traffic is coming from here, for example, in this. Traffic is coming from the what? From the service provider. He sent, what did we refer to this? We refer to this as a what? As a POP. POP stands for what? The point of a presence. Where is that's the switch where they are going to gather what? Where they are going to gather multiple what? Multiple traffic from multiple users, and then they what? They will transport this over over a metro network. Most of the time they are ring networks. Looks like what? Looks like the Olympics. So all of these are ring networks connecting to what? Connecting to multiple POPs within the metropolitan area network. Each one of them is what? Add drop. One more time. What is add drop means? You drop some of the traffic when it reaches what? Destination. You add what? Traffic generated at that point. So you add traffic, you what? Drop traffic, depending on whether they have reached the destination or not. Oops. Did I miss John? Yeah. We already talked about this. Now, I want to show you a solution. Okay, first of all, the core here. Let's see if you can help me here. This is a what? How to connect the metro to what? With another metro. This is a metro, for example, Chicago. This is another metro, which is what? New York City. Clear? Okay. Are they in the same metropolitan area network or different? Which means what? We need to connect them via what? Via the backhaul, via the core. This is the core. By the way, in this case here, it shows a point-to-point. Most of the time, those metropolitan area networks are connected instead of a what? Instead of a ring, they connect them via what? A mesh. A mesh to provide for what? To provide for redundancy in here. Those are all what? DWDM. So in here, if we are using SONET, what are we transporting? IP is running over what? PPP or Ethernet, whatever the data link control protocol is. IP over PPP over SONET. What is the SONET behaving? Which layer? Here, physical layer. But on this network, what is the SONET behaving? It's behaving as a what? As a second layer, because it's going to run over what? Over DWDM. Did you understand that or not? This is the concept of the layered architecture. When you see a block on top of the other block, means what? It's running over it. Now, in this case, you could also eliminate the SONET, and you could what? You could operate IP over what? Over DWDM immediately. But the question here, you need to make sure that this router, the interfaces or the ports of these routers can support the higher rates of what? Of DWDM. Now, when you hear the word IP over DWDM, in reality, it's IP over some what? Over some second layer protocol, whether it's Ethernet or whether it's PPP, over what? DWDM. In other words, you are just eliminating the need of what? The need of SONET. Clear? Clear? No response. Okay. Now, one solution that we will be interested in is the following. Ethernet in the metro or Ethernet in the core. I want you to see this diagram so that you understand what I'm talking about. This is the user computer. Yes? This is the user computer, the user network. Okay. He is using a what? An Ethernet interface. Ethernet interface. He is connected to a what? To a LAN. A LAN, local area network, within the customer network. And he is using a what? A switched Ethernet. Do you remember what is the difference between switched Ethernet and the shared Ethernet? In switched Ethernet, there is no what? There is no collision. Are you following? So this is a what? This is an Ethernet switch. This one is connected to what? To the Ethernet switch. That Ethernet switch is connected to what? To the Ethernet switch located where? Where is this one located? Located in the service provider network. He is running over what? An access network. Now, where is Ethernet is running? Ethernet is running over whatever what? Whatever the protocol that is being used here. So, for example, Ethernet over what? ADSL. Did you get my point or not? When it goes through the ADSL network, when it comes in here, this one will recover the what? Ethernet frame. Yes? He will take the Ethernet frame and he will what? He will change it into optical. This is the optical. This is what we refer to optical framer. You are going to be framing an optical or generating an optical frame. Inside that optical frame is a what? It's an Ethernet frame. Very good. Inside that optical frame is a what? It's an Ethernet frame. Transport the optical frame over what? Over the DWDM, for example, or over SONET. And at the other side, what do? You get rid of what? The optical frame, you recover the what? Ethernet frame. And same thing with this. That's another one, another one, another one, and so on and so forth. OXC stands for what? Optical cross connect. To connect to this switch, or it can connect to another switch, and so on and so forth. To the what? To the other side. The other side is the access network. Do you follow me or not? Yes? Everything is what? Everything is Ethernet. In other words, the end users, because this one is what? This one does not need an optical interface. He only needs what? An Ethernet interface. He is connected to this. We call it what? Ethernet in the metro network. When you hear the word Ethernet in the metro network or in the metro carrier, does not mean that the medium is what? Ethernet. The medium is still what? Optical. But the frames are what? Are Ethernet. Did you get my point or not? So you are taking the Ethernet frame and you are encapsulating it into a what? An optical frame. All of them will only see a what? End-to-end Ethernet. All of these are what? Transparent. The optical is transparent, is within the network itself. Clear? Oh, and we will talk about that. Later on. This is, I think I showed you this last time, the economy of the DWDM. Instead of extending, for example, in here, extending multiple fibers, and you put a what? An amplifier along the way. Every 40 kilometers, you put a fiber. Sorry, you put a amplifier along the way. In here, you use a what? A single fiber. You can what? Save on the number of fibers, and you need to save. You can save on the number of amplifiers as well.
Dr. Zahid, this is a 5-minute warning.
Okay. Already talked about this. This is a summary of the networking infrastructure, both in the access and in the web. Now, let's look at the users. In the users, what do we have? We have a local area networks, a switched Ethernet, a wireless LAN, the 802.11, UWB, anybody? The ultra-wideband, this is again another type of what? Another type of wireless access using but operating at a large band in the 50 to 60 gigahertz, sorry. IR, anybody? Infrared, and the Bluetooth. You are all familiar with the Bluetooth. All of these in the user. In the access network, we already covered PON. T-carrier service, what is that? That's the T1 and the T3 that we just talked about. Yes, we call it the T-carrier service. The T-carrier service is basically for what? The corporate users, not for the residential users. It costs too much money for the residential user. Clear? Okay. The cable data, like I just told you, subscriber line, and so on. 802.16. What did we call it? That's the WiMAX. Clear? That's the access, WiMAX, from your residential to what? To the high tower, like I showed you a moment ago. 802.16.
The time is 14 o'clock.
The access via satellite. LEO stands for what? Low Earth orbiting satellite. This one did not seem to be successful. A lot of companies came and tried to install a low Earth orbiting satellite, but they went all bankrupt. So it was not successful. The current successful satellite systems are the GEO systems. Always remember, as the satellite becomes what? Higher and higher in the altitudes, the coverage or the footprint becomes what? Becomes larger and larger, which means you need less number of satellites to cover what? To cover the Earth. And why do they call it geosynchronous? Because that orbit is rotating at the same speed as what? As the Earth. So they seem to be what they seems to each other as what? As fixed in location. Now, in the metropolitan area network, again, cellular mobile. Cellular mobile means what? Means the third generation, fourth generation cellular, and so on. SONET rings are RPR stands for resilient packet ring. We'll talk about this later on. 1 to 10 gigabits bits per second Ethernet is the one that I just showed you. In the core, basically a what? A DWDM. It's basically a DWDM type a transport mechanism. We want to make it extremely fast. Why do we have satellite here? On the long haul, you might need to use a what? Satellite. When you make, for example, traffic generated in the U.S. and destined to what? Destined to overseas or something like that, you are going to go over what? Possibly you are going to go over a satellite link. Clear? Okay. Now, this is the next set of charts, which we will cover quickly next time. It shows you a little bit of history of what evolves in the internet. How did the layered architecture evolved, and so on and so forth. We will do that next time. And you will see most of the changes in the internet occurred. Can you guess which layer? The physical layer and the what? Application layer. Most of the changes. In the other layers, for example, the IP, even though we will discuss IP version 6 in this class, but it's still not deployed all over the place. In some places are deployed, but not all over the place. Routing protocols, the major one is the BGP. BGP stands for the Border Gateway Protocol. It's not a new protocol. It's not a new protocol, but it's a resilient one. It has been used for so long. TCP, it's not a new protocol, but it's still what? widely used. A lot of problem with TCP, especially over wireless link, that we will discuss. Major difference or major changes in the internet or in general in the broadband occurred in which layers? Layer 1, which is the physical layer, the DWDM and so on and so forth, all of these that we talked about a moment ago, and which other layer? The application layer, developing those applications that are bandwidth intensive, that they require a larger bandwidth, video on demand, the gaming, the video conferencing, the high definition TV, and so on and so forth, all of these.
Professor, you are now out of time.
Okay, well, we'll continue this next time. Now, I will be posting the first homework tomorrow, and the first homework will be problems on probability, on queuing, something like that, to judge your knowledge about 503. And from it, I will decide on how to proceed with the setting up some extra sessions to review 503.
This concludes EE 555 with Dr. Zahid. It's January 16, 2014.
One is for the QoS, for the passive